project already 20 years ago. Yes, 20 years ago. And so actually most of the other organizers got stuck because the airport was closed because of fog. So yes, so we are only few. So I hope they will do it, because I mean one guy had problems, so I am ready to do another lecture. Yes. I had to do another lecture for this guy this afternoon, and I hope that they will arrive, because otherwise I have to do all the lectures of the school. So, I mean, 3 lectures is already enough. So, how is the school organized? So, I mean, it's not a job. I will tell you in the introduction. It's not a job, because it's like one has to go from 0 to infinity in 5 days. Velocity is infinity, of course. And so the idea is that in the morning we will do theoretical lectures, and also there we will try to introduce a few concepts, but not everything, because it will be impossible. You need a course. And then in the afternoon we will do hands-on, so you will see those things in practice using Yambo. Of course, during the school you will see only bits, and it's just, I mean, an invite to just go back and learn more. So, but the structure is exactly this. We have theories in the morning and practical lectures in the afternoon. All developers will be just around. I mean, I'm staying in this guest house, so whatever you need, just come to us for installation and problems and theory and everything. Just come to us, and then we can discuss. Okay, so let me open officially the school with a small lecture about the perspective on material science that is given by Yambo. So if you look at material science for Yambo, what do you see? I think that the perspective of Yambo is just a perspective of materials community, in the sense that you see all critical aspects and features and needs and problems that you encounter in doing computational physics. Okay, so material science is, no, this is too much, was it? Yeah. Material science is a very large word. There are many different communities inside, and actually I'm a theoretician originally, personally. So my background is in quantum field theory originally. Then I moved on condensed matter. So I come from this part, theoretical physics. And then I started writing the code because I needed numbers, just numbers. Fine. But the point is that along the years, in the last 20 years, the world around the theoretical physics increased enormously. And now there are communities that themselves have an entire literature and research and so on and so forth. Things that are very far from our background. I know about your background, with chemistry or physics, but there are things, just trust me, in this theoretical computer science, in computer engineering, that I understand nothing. I mean, it's like if someone talks to me in Arabic. No way. But at the end of the story, I have to take care of all this, because the codes like Yambo have been involved in all different communities, in all these communities. This is really source a lot of complications for me and also for you as users. I mean, it's not that you install Yambo and then this afternoon we will be able to run on 60,000 cores. No way. I mean, it takes some time. It's not straightforward. Okay, so there are different actors in this world of material science. So there are experimentalists, theoreticians, and what I say, runners. I mean, so just run on computers. So theoretical physics. This is what we will learn in the morning. And the problem is very old and very well known. Your Hamiltonian as a body-body interaction. Column interaction is not single body object, it's many body objects, so whatever you want to do, you have to take into consideration the effects on all the electrons together. So how do you solve this many body problem? This is what is solved in the theoretical part of the story. So you need to find methods like density functional theory or many body perturbation theory or beyond. I mean, we will just tell you about few methods. This is not all the methods have been developed. We will not talk about, for example, dynamic and mean field theory. We will not talk about that. So we will just talk about the tools and the approaches used by the code. So the first part is, yes, how do we solve it? And then once we find a way to solve it, how do we implement it? So we have some equations to solve, and then some approximations to do. And moreover, the kind of theory that we want, I'm just giving you an overview, I mean, you don't understand everything. The kind of theory that you need depends on the physics. It's not that you do theory yourself, I mean, in an absolute way. It depends on what you need to calculate. If you need to calculate current, or a voltage, or a charge migration, or a polarization, an absorption, a gap, you name it, and then we have to sit together and see what is the theory needed to evaluate it. And depending on the kind of physics, you may need to introduce more complex and advanced methods. That can be TDFT, many-body, or even more complex methods like non-equilibrium Green's function theory. This is what I'm doing at the moment, for example. I'm working in equilibrium Green's function theory world. Good. Then, once you write your beautiful piece of code, and this is what it was done myself in 2000. Actually, I started writing. It was not Yambo, it was name of self. And I did it for my PhD. I needed a tool to calculate the numbers in my PhD. But along the years, many people contributed to the code, and it grown and grown. And now we are version 4.5, I think. And along the years, it got a lot of more things that were calculated with the code. I mean, we stopped in 2009, so there are still 10 years. There are so many things. And then you can get a clue, an idea, just for the fact that at the beginning, in the first paper that we published, when the code was made GPL in 2009, we were 4. Now we are 20. In the last papers we published last year, we are 20. Okay, you will see a lot about Yambo. Yambo can calculate several things. I mean, it is fed by a DFT ground state calculation. At the moment, we support PWSTF and a BNet. So you do your system with those two codes, and then you are ready to calculate, to start Yambo. And then with Yambo, you can calculate plenty of things. And then there are several libraries that they are released with the code. So in general, we try to use it as most user-friendly as possible in the compilation installation. Even if my student says that this is something that it's friendly only for me, it's true. I mean, but we can do it together. And many people, and then actually it has grown in the years, and now it's not only a code, only as a community. So we have been doing schools in the last 20 years, and Yambo has traveled. I think I miss Australia. I think Australia, because China, Japan, Africa, United States, North, South, Europe, I think everywhere. Maybe Russia. Maybe we miss Russia, maybe. Now for the rest, it has been told all over. Also thanks to ICTP, we participated to many schools organized by ICTP. And, there is a forum, there is a wiki page, that is the one you will use to do the tutorials, where there are all information about the code. This is the educational part of Yambo. So there are how-tos about the tutorial, theories, and so on and so forth. And the source is open and is also in a JIT repository. So if you want to contribute or to get the latest snapshot of the code, you can use it. If you're able to use JIT, you can use JIT. If you don't know what is JIT, just ask us, we will tell you. And it has been applied, I mean, we are around 600 publications that have been done using Yambo, and they are practical about everything, from molecules to solids, nanostructures, surfaces. Actually, I don't even know all the system it has been applied to. Being a community, it has several interactions with funding. It has been source of funding, it received funding. At the moment, there is in 2020 projects. And lately, we have been a lot concerned about performance, because you know that now computers, in the material science world, I mean, the part relative to computers has grown enormously. And also the technology in computers has grown enormously. So for example, now the latest machine, and Andrea will tell you more, the latest machine, the most expensive and fast and enormous at the moment is not only CPUs. It's probably an hybrid machine where there are CPUs and GPUs, video cards, you know, the one used for gaming. I bought a PC to do coding on GPUs, and my sons, they like very much to do Fortnite. They saw and said, "Wow, but this is great to play Fortnite," because actually we're using the technology developed for gaming. I mean, those NVIDIA cards, and so performance is an issue, especially for us that we are theoreticians. I mean, at the beginning I didn't have any idea what is even a GPU. So yes, we are many. We had a T-shirt, even if most of them lost it, but it's a T-shirt. Yes, and so we are many. We had several schools around, and this is the last one. I went in Cameroon in last November. Then there is this school. Then this year again we will go in Africa again, in Rwanda, in summer. But there are many. I mean, 20 years there are really many. Then we have educational. Okay. Just as the last words about the performance. So what makes Yambo specific is the fact that among all the codes that were, I mean, when I did my PhD, there are many people writing codes. But at a certain point, where does supercomputers enter in the business? Lots of codes were not able to cope with it and were not able to run on those machines, because actually you need sometimes to rewrite entire parts of the code. Yambo, for some reason, was able to do it. I mean, it was rewritten. I mean, between version 1, 2, and 3, was completely rewritten. Then now it's not possible anymore. It's too large. There is no way to rewrite Yambo now. You can rewrite parts, but not the entire code. And this is possible because the code was modular. I can tell you. I mean, there is also some theory of coding. I mean, it is not that you do coding. I mean, just that's it. And one of the key things to be able to evolve is to be modular. If you're modular, you have pieces that are as much as independent as possible, then you are most probably to be successful. As I told you, in the years we managed to export Yambo on CPUs and GPUs, and this is the latest development. I mean, the latest release only is the first one, the 4.5 is the only one that has been released with GPU support. And then, thanks to this kind of coding, we were able, this is actually already old result, able to run up to 60,000. But I mean, actually, Yambo at the moment is pretty good in performance. We didn't manage to see a saturation of the code. And indeed, in one of the 8 projects where this is a project for exascale transition, how to bring those codes to exascale machines. Okay, so again, MPI and CPUs, you will be told how to use CPUs both as MPI or OpenMP. There are 2 different methods to use the CPUs, while GPUs, there is only one method. And this is performance about GPUs. I don't want to learn too much about this. Okay, Yambo is pretty much used among the codes in the Praise and in this H2020 Max project. Yambo is the second after Quantum Espresso. And then, yes, I want to just say a few words about something that for me is really important. I mean, the situation is super complex, right? So theory and coding is a big jump. Then how do we do it? I mean, how do you do it? How do you find yourself, your path in this walk? So what I suggest after many years of teaching is that you have to use a gradual procedure, but you have to be careful. The idea is here. So you have a physical phenomenon that can be among the ones calculated by Yambo or another one. It's possible that you came here because you want to calculate, for example, charge migration. At the moment with Yambo, you cannot have electrons moving in space. Let's talk about that. Then, physical phenomenon, you need to, first of all, read and study. So if you run, this week, everything will be, I mean, just reshuffled because of the time. But when you go back, don't run before reading. It's completely useless. Then you fill the form up with questions that are completely nonsense. So you have the theory, study, and then the simulation is at the end. Because between the theory and the simulation, there is one important step. It is discretization. Computers are discrete objects. Computer is not continuous objects. So if you have an integral differential equation, you cannot put it as it is on a computer. You have to discretize. And in this discretization, there is the source of most of the parameters. So you study the phenomenon, you connect it to the microscopic world and to the theory, then you understand which kind of numerical methods are used, and then at the end you simulate. So from this, you can approach in the proper way hands-on tutorials, understanding the parameters, the way to choose them, and I mean, it's important that you understand, because there is, in the tutorial, there is more than one example that if you don't change properly the parameters, you will stuck the machine. In Cameroon, it happened to me. That's the point. People say, oh, my computer does not reply, does not answer anymore. It's completely frozen. I said, yes, because you didn't change that number. So Yambo can kill your machine, yes. Okay, then maybe, okay, because then is the point, everyone asks me, why you are oyster? Why it's an oyster? Then Yambo doesn't mean anything. So even there was Conor Rogan that, to make a joke on me, said yet another many body code. But Yambo doesn't mean anything. It's just I mean, in Africa, in Swahili, Yambo means hello. That's all. Why the oyster? The oyster is because when I started writing this Yambo, when I met actually Mita, as one of the founder of the code, I was working with vacuum polarization diagrams. I had those diagrams all around. I mean, I was just crazy with those diagrams. I mean, because I couldn't find the solution to the problem. Then I found the solution because I published a paper, but then she turned the oyster, the vacuum polarization diagram, the second order vacuum polarization diagram, in an oyster. And this is why Yambo is as an oyster. That's it. Okay, so, yeah. That's the easy part. No equations. Good. Now, how is the story? We have in the program, there is already many body. Okay, so do you have questions about this? No. You have to wake up at a certain point. I mean, just to inform you. Okay, so let's go to the real job. Now we do many body. Okay, what time is it now?
10 to 10.
Oh, we are in time. I was quick. Okay, because in general I'm not quick. I'm very slow. Okay, so let's now do with the many body. Amen. Hey. Hey. A second. Yes. Okay, so at the very core of Yambo there is quantum mechanics. Now, is there any one of you that doesn't know what is a bra or a cat? Just to know, as chemists, I mean, how you are distributed? The chemist just can raise the hand? Chemist. Okay. All the others are physicists, it is in engineering? Physicists, all the physicists raise the hand? Okay, so chemists and physicists. Oh, a very minority of chemists. Okay, will be an odd life for you, I know for the chemists, but we will help you anyway. Okay, so, but chemists, I mean, you do brackets, right? Yeah, so Hartree-Fock, yes, Hartree-Fock is fine. The problem is after Hartree-Fock. Hartree-Fock, you go for MP, whatever, we go for GW. Yeah, I know. Okay, but I mean, let's do now a quick review of quantum mechanics, the easy things that we need for Yambo, and then we will introduce many body in a heuristic way, so a simplified way. Okay, so quantum mechanics make short, then the many-body problem and Hartree-Fock. Why Hartree-Fock? Because I think that Hartree-Fock just can give you a very good insight about the different paths you can take to solve the problem in a weakly correlated case. Okay, so the problem we need to solve is to create a micro-macro connection. So you have your Hamiltonian, that actually this Hamiltonian is just the purely electronic one. But in general, there are a lot of other actors entering the Hamiltonian, like phonons or spins or magnetic fields, electric fields, and so on and so forth. But, I mean, the core of the many-body problem is already inside the electronic case. So now you need to find a connection between this Hamiltonian and the observables. In this case, there are 3 observables that you can calculate with Yambo. You can calculate band structures, you can calculate width of the structures, positions, optical absorption, including temperature. You can include temperature with Yambo, with electron-phone interaction. And you can also calculate time-dependent quantities. In this case, it's polarization. Time-dependent polarization through many-body and also through the Berry approach. How do we do it? That each of this somehow is an observable. In the easy cases, you can really write it as an operator. That can be, I don't know, the current, the polarization, and also the bands. They can be connected to averages of operators. So you introduce this space of states. So given the Hamiltonian, the eigenvalues of this Hamiltonian eigenvectors define a space. This is an orthonormally complete space on which you can calculate averages, and also time-dependent averages. So you can introduce a time-dependent operator switched on in interaction, and this system will start oscillating. And on the basis of these oscillations, you can calculate quantities. Then the very hard job is to rewrite this very compact problem to expand the problem. Because, I mean, when you define the observable as an average of an operator, you are condensed as super simple. It's just one line. But to calculate it and to discretize it, you have to make it explicit. This is the work of theoretical physics, to write this condensed average in terms of something that can be calculated. One way is through diagrams. This guy is Freeman-Dyson, the Dyson equation. And the Dyson equation is a way to rewrite specific case or specific average in terms of a series, of which you can calculate analytically the terms. And then you're done. If you manage to sum this series, you are done. You can really calculate at the end, get a number. That's the point. Now, what is the complicated part about this term? And you will see in a second. This first part, you see, is a summation over the electronic states, the electron, sorry, I is an electron. You have an Hamiltonian of the single electron. So this first part represents an electron moving alone. If the electron moves alone, then the solution is just to find the spectrum of this Hamiltonian. But this is the beast, because it will just fill electrons moving reciprocally. So this means actually that in this room, in independent particle approximation, if some of you the phone of some of you will ring, the others will not care, will not see, will not hear anything. They will just look at me. Instead, the many-body interaction will do in such a way that if your phone will ring, some head will turn. And actually, the heads will turn depending on the distance. Unfortunately, the Coulomb interaction is really a beast because it's very slowly decaying potential. Very slowly. I mean, in transfer moment, in transfer space, it goes like 1/2 square. It's even divergent. So slow to be divergent when you do the Fourier transform. This is source of a lot of problems. actually it's also source a lot of physics. I mean, nature works. I mean, if you look at nature from math, you see that the most interesting things in nature, in math, are divergences, like 1 over q squared. So you have plasmons because of the 1 over q squared. Okay, so the many-body problem is the problem of connecting the eigenstates of the full Hamiltonian to the eigenstates of the single particle part. So we define this lowercase n at the eigenstates of h, of small h at single particle part, and at uppercase n, the eigenstates of the whole Hamiltonian. Then again, you have a ket that is a state, and a bra is the adjoint. This is fine, right? Yeah, this is okay. Okay, this is all you know. Yes, and then you also know that if this operator commutates with the Hamiltonian, then it's stationary, and then the average is just simply the corresponding eigenstate. Good. Okay, now, the easiest way we can do is just to neglect the interaction. If we neglect the interaction, then we approximate the Hamiltonian with only the independent particle part. So in this simple cartoon, the interaction are those lines. Every electron is this yellow sphere, and the interaction are the lines. If you remove the lines, then the solution is trivial, because the state, the exact eigenstate of the full Hamiltonian is the exact eigenstate of n independent electrons. This is just a product of the single electron states. This product is averaged with a function representing the level of excited state. In the ground state, we are all sitting in the first excited state. Some of you are just up in the air. So it's just a way of counting the single particle levels. It's trivial. I mean, if you have a finite temperature system, what would be the weighting function? Sharp question, yes. Yes, if you have excited state of an independent electronic system at high temperature, what is the function? It has two names. One is Italian, and the other is Iraq, is Polish. I mean, if they are bosons, if they are not electrons but bosons, the function is of the name of a very important Indian guy. Yes, the Bose answer is for? Bosons. Yeah, for fermions? Yes, it will be a Fermi-Dirac function. So dependent particle approximation to excited states in the sense of temperature will be a Fermi-Dirac. So yeah. So in this case, you can rewrite this complex average as a functional of the averages in the free single particle states. For example, the Hamiltonian of the ground state is the sum of the occupied energy levels. That's it. It's easy. And then you will see that we will show you how to calculate several quantities in this independent particle approximation. It's easy. Everything is practically analytical. And okay. Then, I mean, one important point then you will see along the lectures. Why, I mean, is it always so bad, the independent particle approximation? Well, it depends. Indeed, first you have to understand the physics. We go back to the original argument. We have to understand the physics. And then compare what you're calculating with what you're interested in and see the level of approximation, unless you don't have formal proofs that the approach you're using is the exact one. You have to use this, let's say, validation with check with the experiment. You understand more about this. But actually, I think that 99% of the things that we are going to talk about, we don't have formal justifications. Good. Now, in the real world, the Hamiltonian includes several effects that we will neglect for the moment. Because in the full Hamiltonian, there is also temperature, there are phonons, there are also other kind of actors, can be magnons, can be spins indeed. And every of this element introduces an additional interaction term in Hamiltonian. So for the moment, we neglected Fourier electronic. We stick to the zero temperature. So what I will talk to you today is zero temperature problem, because of finite temperature, the tools change. And also we will use a static Hamiltonian for the moment. We will not introduce a time-dependent fields. And we will restrict to the ground state. Okay, so in this case, the core of the many-body problem is the following, as originally introduced by Landau. So you have those free electrons are bare, and then you have the full interacting problem. Is there any way to replace the single actors, the single electrons, with something that is slightly modified but still weakly interacting? So if you want, yes, if the phone will ring, we will all turn our head. But if the person with the phone has an overcoat, you know, or a big pullover that is actually shielding the phone, then the sound, the music will be weaker, right? And then maybe only a few persons around will turn head. This pullover is a way to dress the electron. So how do I define and how do I know if it exists such a representation? So in the many-body methods, the idea is, from a formal point of view, is to replace this Hamiltonian not with the free one, but with the free one with, in addition, a many-body potential. It's a single particle many-body potential that is not produced by nature. It's something that you introduce mathematically, and then you require to this potential to satisfy some condition, to reproduce something of the full Hamiltonian. What? Now we'll see. Then with the Hamiltonian, we'll also introduce, in the case of time-dependent Hamiltonian, a time evolution, but this, let me skip it for a moment. No, let me skip it. No, I will go back to this later. One problem, how do you approach this problem or define this potential? Who of you doesn't know anything about EFT? No, little. So little. Okay, yes. Okay, that's good. All the rest, you know what is DFT. It's okay, and it's important for us because then if I give DFT for given, then you understand nothing. Wow, only one doesn't know Honenberg-Kohn theorem. Would you be able to tell at least what is it talking about? What, Fulvio, my student? I mean, you should know. Come on. I will ask you later. So Honenberg-Kohn theorem. Who has nothing? Who doesn't know it? No. Okay, only one. Okay, so you just a little bit. Okay, that's fine. So density functional theory is a method to define this potential, and it's a variational method. So one way is a variational way, and then we will just mention it. But the straightforward method that you will find on a textbook is to use perturbation theory. This is the poor man approach. You say, oh, look, I multiply the interaction with a prefactor, and then I do an expansion. I assume that I can expand the eigenstate in powers, and then I define the coefficients in such a way that to a given level of approximation, the two states are the same. This is perturbation theory. If you do with two-level problems, you can have, this is the two-level independent particle part, then you add a potential that just mixes 1 and 2. Two levels, 1 and 2. This is really straightforward. You can do it. I mean, you just do the expansion. You can solve exactly and find this. But then you can also take this, this thing, and then expand the powers of lambda when you multiply v by a lambda. And then you get that you can expand the exact eigenstates in powers of lambda. Now, of course, in this case, you solve exactly the problem. It's 2 by 2. Then you multiply v by lambda, and you do power expansion. Then you see, yes, I could just expand in powers. The many-body problem is that there's a case where you cannot solve exactly the problem because you cannot solve exactly the full Hamiltonian. So in that case, you use perturbation theory. And perturbation theory is trivial. You expand the eigenstates, and then you require the theory, you require the expansion to give this the eigenstate, eigenvalue problem explicit. Then you expand in powers left and right hand side, and you compare term by term. By comparing term by term, you find an expansion for the eigenvalues and for the eigenstates. This is the static perturbation theory. And again, using static perturbation theory applied on the 2x2 level system, you just get this expansion. Again, we are not at the point of getting a potential. We are saying that with static perturbation theory, given a certain perturbation, this will modify the state and the energy, but then you may wonder, where is the potential? Now, to introduce the potential, we use Hartree-Fock. I think Hartree-Fock gives at the end two interesting concepts that can be used in general, very much beyond Hartree-Fock. So what is Hartree-Fock? Hartree-Fock is a way to solve the many-body problem within certain stringent approximations, assumptions. In the case, and then you can introduce Hartree-Fock in two ways. One is with the perturbative approach, and the other is with the variational approach. If you do it with the perturbative approach, Hartree-Fock is just easy because you take the independent particle part, then the ground state of this Hamiltonian independent particle part is just a product of states, and the eigenfunction is a Slater determinant. And then, exactly like in the two-level problems, you do perturbation theory calculating just averages, exactly like in static perturbation theory. You go in powers of the interaction. So at the first order, you have the correction, and the second order, you have the second order correction. Now, when you solve I don't want you to get all the math, because it would be impossible. Just get the ideas. You do perturbation theory, then you correct the energies. Then you go and look at the definition of the ground state energy at within this approximation. You see that, again, it's a sum of single particle energies. In Hartree-Fock, if you do Hartree-Fock, you do the math, you realize that you can rewrite the ground state energy with the interaction treated at the first order. So you take the interaction, you treat it to the first order, then you realize that your total energy is a sum of single particle energies, but they are now modified. So this change in the single particle energy can be written as an average of a potential. You can introduce the potential in such a way to give the change of the single particle energies within second-order perturbation theory. This potential is composed of two pieces. One is this part that we call Hartree, and the other is this other part we call exchange. The Hartree part is something you should have expected from simple physical arguments, because the Hartree part is just a potential produced by the density of the system. Beyond the single particle approximation, where you have only the kinetic part, the first term that appears is just the standard electrostatic potential. This comes out so naturally, in the perturbative approach. In addition, there is another term that is the Fock term. This Fock term is instead induced by the form of your eigenstates, that is Slater determinant. The B antisymmetric, it just avoids electrons to fill fermions to overfill a single state. So it's not possible for two fermions to be in the same position. So it's Pauli exclusion. What is really important of this approach is that you have, even if within severe approximations, Hartree-Fock, we've written the many-body problem as a single particle problem under modified potential. You can actually found Hartree-Fock through a variational approach, completely different in nature, where you actually assume that all the ground state of this Hamiltonian will be a superposition of Slater determinants, and you find this superposition in such a way to minimize the energy. If you do it, you use the Lagrangian approach, then again, you find an equation for the single particle states of the ground state Slater determinant that solve an equation that is the Hartree-Fock equation, where again you find the Hartree and the Fock potential. Now, there is a big difference with the perturbative approach. in the perturbative approach, the states that enter in the potential itself are bare, because it's perturbation theory. So you take a system that is non-interacting. With this non-interacting system, wave functions and energies, you build the potential that will normalize the electrons themselves. So you see, this M naught is the bare level enters in the potential, and this potential will change the energy of this bare level. So the change of my energy depends on myself, and depends on all the others. It's a self-consistent problem. So again, in the simple example I gave before, in the pullover of the lady, we are all involved in creating this pullover. So, but we must be dressed as well. So we are bare, we build a first version of the pullover for all of us. Then again, now with the pullover version 1, we build up another pullover, version 2. This is a self-consistent cycle that Hartree-Fock has built in. It is an important concept because you see that in many bodies, if you do perturbation theory, you have bare objects inside the definition of the potential. If you do with the variational, instead, the objects inside the potential are already dressed. So take-home message. In Hartree-Fock, so you have Hartree-Fock, and this is Pauli. So in the Hartree-Fock problem, you have just physically a simple introduction of electrostatic and exclusion principle. So not very much fancy. But there are important properties that we must take home for going beyond. First is that the perturbative approach, if you introduce Hartree-Fock with the perturbative approach, energies and wave functions, energies will change, but wave functions will not change inside the potential. In a variational approach, everything must be found self-consistently. But again, in both cases, the Hartree-Fock potential defines a potential, an effective potential, that exactly gives the single particle levels that correspond to a variational minimum in a variational approach, or to a second-order perturbative correction in a perturbative approach. You say, now, wow, Hartree-Fock is great. Then you apply Hartree-Fock, and you get that the gaps of your systems are systematically overestimated. And lead infrared, I think, is like 5 eV. You are above of 5 eV. So you're completely off. No way. I mean, but this is something expectable. I mean, actually, chemists will tell me, no, Hartree-Fock is not so bad. Yes, it's true. If you take a system, it's very tiny, it's not solids. If you take a system that is only few electrons, then their other effects are important. So in the case of few electrons, then Hartree-Fock is particularly efficient because in that case, what really makes a lot of difference is the self-interaction. So we are only few, that is I can explain you. But I mean, anyway, Hartree-Fock for few electrons is particularly much more effective than in the case of extended system. For extended system, it's pretty bad. So this means we are missing something. What we are missing, and this is Feynman, because what we are missing actually is easily connected to Feynman diagrams. We miss correlation. We miss correlation. So correlation is what is missing when you do just Hartree-Fock. I mean, also, the point is that physically, now we have problems, because how do we introduce in a conceptually simple way correlation? Now we are just introducing as something that is just missing. Now in the next lecture, we take 2 minutes break. In the next lecture, I will try to introduce correlation in a simple way, with an heuristic approach, without introducing diagrams or something like that. But at the moment, what is important of this first part of the lecture is that the take-home message is that in many bodies, really, the problem that we have to solve is to define in as much as easy possible an effective Hamiltonian, an effective potential, an effective whatever, that still keeps the solution of my problem to the level of a single particle problem. Of course, this potential, I have to be careful, because in Hartree-Fock, this potential, there is no way, it is defined by the method itself. When we introduce correlation, we need to be careful in the sense of filling this potential with properties that are interesting for our problem. But still, the problem will be to introduce a potential that will embody within some ways the many-body properties. Okay, so now, what time is it, Andrea? Sorry? 10:20. 10:20? Okay. Now, I don't want to do a 40 minutes lecture. I prefer to do smaller lectures, so we will do correlation after this. And now I would like to have discussions. So if you have questions, if you don't understand anything, if you want to rest 5 minutes, this first part is done. Also, so in this way, I think you will be more awake. So if you do like 1 hour lecture, in general, also me, after 1 hour lecture, after I just decay, I just sleep. Instead, with the 20 minutes, then. Yes, yes.
I know you didn't really want to elaborate on this too much, but I'm actually really interested in the self-interaction error because I've heard it so many times, but I still don't fully understand.
Okay, yeah, sure. It's I mean. Oh, Andrea, can I tell you even more? Andrea, you want to comment on the self-interaction? Andrea is an expert.
So, in the sense, I think that self-interaction, there are, as far as I know, at least several definitions in the literature. I think that there's a very different case for what concerns density functional theory and many-body perturbation theory. And in a sense, the case of many-body perturbation theory is somehow easier, since if you have Feynman diagrams, somehow you see exactly what happens there in the electron-electron interaction. By this I mean that typically, so if you start from expectation values of the electron-electron interaction operator, which has 4 field operators, you end up with direct and exchange terms that, when applied to same single particle state, basically would cancel out. So somehow in this respect, Hartree-Fock is prototypical. You have the cancellation of the Hartree term with the exchange term. Yeah. And somehow, so one of the definitions of self-interaction is exactly when you go to higher levels or higher orders of theory, the fact that in some cases you miss some of these exchange diagrams that may cancel out the corresponding direct diagrams. And this is exactly what happens, by the way, in the GW case. So in the GW case, you have screened interaction, and the diagrams you miss are already there at the second order. So in GW mix the second order exchange diagram, and in fact you suffer of self-interaction. That kicks in via the screening, the RPA screening, that is also well known in chemistry to be not self-interaction free, and actually you have what is self-screening within GW. This was documented both theoretically and computationally. Things are instead different if you think at the case of density functional theory, where you don't have such information of diagrams. So somehow you have the hood of your car that is closed, and you cannot access that piece of information. And in that case, you have to recur to other definitions of self-interaction. One of these was basically relying on an exact property of the total energy as a function of the fractional number of electrons, that is piecewise linearity of the total energy. That is somehow connected, since the derivative of the total energy with the occupation is somehow related to an effective eigenvalue, single particle eigenvalue. So somehow the fact that total energy is piecewise linear means that these eigenvalues do not depend on their own occupation. That again is a concept related to self-interaction. Still is not the very same definition, such that the Hartree-Fock that is totally self-interaction free from a diagrammatic point of view is not self-interaction free in the sense of piecewise linearity. Still, in density functional theory is somehow the only thing you can do. You can only define total energy self-interaction in that framework. In general, this was referred by, I think, Purdue groups at least, as many body and body self-interaction freedom. And to me, that is so the proper definition in density functional theory of self-interaction is still an open options. There are several proposals there.
If I may add a very simple old man's compliment to what Andrea just said. It's not very rigorous, very theoretical, but to me the self-interaction error is the name you give to the feature of your theory that makes the energy of the hydrogen atom different from one Rydberg. So if you have a complex theory, such as many-body theory, the minimum requirement, or density functional theory or whatever, quantum chemistry, you name it, couple clusters, anything, the minimum requirement you have with such a complex theory is that it can solve the problems that you could solve without that theory. Unfortunately, none of those complex theory can solve one-body problems. You don't need them in those cases, but it would be relieving if you could. And so this is not a definition, but if you do density functional theory for ordinary, of course, Hohenberg and Kohn say that you do density functional theory for one electron, it gives the right result. It's a theorem. But current implementations of density functional theory applied to one body problems, to one electron problems, give the wrong energy. The name you give to the mistake you make is a self-interaction error. So a little bit, a step further in elaboration is coming to what the other Andrea said in his lecture, that these theories, Hartree-Fock and density functional alike, are mean field theory, or mean field-like. Hartree-Fock is indeed mean field, density functional is not, but it has the form of a mean field theory, which means that you can attribute physical properties to individual electrons, which you cannot in a truly interacting system. So that you can speak of properties of individual electrons in mean field theories. So you are tempted to treat one electron at a time, as you would do for a hydrogen atom, for a one electron. Formally, mathematically, they are the same. Elaborating a little bit more, so the self-interaction error in density functional theory and in many-body perturbation theory and in any sophisticated theory is the relics, what remains of the original sin of those theories that fail for the hydrogen atom.
Okay, so how do we do? I mean, I have to do correlation, then it takes 15 minutes to do correlation, then we go for the coffee break. Or, because now is, what time is it now? Now is, it's 10:30 now. 10:30, oh, is the plan? Coffee break. We do coffee break and then we do correlation? Huh? Okay, okay. Okay.